In keeping with the blinking LED theme, I thought that in this video I would show you how to blink, in this case 6 LEDs, and only using 3 I/O pins from the microcontroller. So how I actually do it, I'll just move this out of the way here and show you a schematic. So these are the 3 I/O pins. There's a resistor on each of the I/O pins, and then you can see how these LEDs are hooked up. So between each pair of pins there's a pair of LEDs that are pointing in opposite directions. So between these two pins you've got these two diodes, between these two pins you've got these two diodes, and then between the outside pair of pins you've got these two diodes. And what you do is under software you just control the data direction for each of these pins, whether it's an input or an output, and also whether it's high or low. So if we just look at these two I/O pins here, if we wanted to eliminate this LED here, we could turn both of these I/Os into outputs, make this one low and this one high, so it would drive 5 volts through the LED and through the circuit here, and it would light this LED. Keeping these both as outputs, just change the states of both of them. So this one's high and that one's low, this LED lights. And similarly with these two, or actually let's go back to these two again. With these two outputs, you don't want to have this one an output being driven low or high, because you're going to end up in turning on one or the other of these LEDs as well. And so you make this one an input, so there won't be any current flowing in either direction into this pin. And then if you want to turn on these two LEDs, make these two outputs and this an input, and then you just drive the states of these two pins to make whatever LED to go on and off that you want. And the same with the outside pins would be outputs, and this one would be in the inputs, would be an input. And so that's how you can drive just one LED at a time. And that's the advantage of this is it only takes 3 pins to drive 6 LEDs. The disadvantage of this is that you can only really drive one LED at a time. That's the best way to operate it. If you needed to do 2 at a time, there's only a couple of LEDs that can be driven at the same time. And for example, if this is high and these two are low, then this LED and this LED would turn on. And you'd have to really work it out if you wanted to get more than one LED on, but you can't get them all on at the same time. So it could be used in a project as a series of indicator LEDs that indicate the state of whatever the microcontroller is doing. And the example I can think of is a washing machine, and so each light could indicate what wash cycle that the washing machine is on, and that way there's only one LED turn on at a time. Now we'll go into the code here and have a look at how to do this. And I'm going to the code is still very simple. It's a bit more complicated than the last one that we did, but it's still very simple. But I want to introduce some Boolean Algebra, or binary mathematics, if you want to call it, because that's how we're going to manipulate the bits in these registers. Now C has some operators, they're called, like well, plus and minus and divide and multiply. Those are operators as well, but we're going to look at some operators that work on the bit level of the numbers. The first operator that I want to look at is called the bit shift, and there's 2 of them, and they're written like this. So this is bit shift left, and the other one is bit shift to the right. I'm not sure how well that's showing up. And the way they're written in C is that you'll have a number. How should I do this? This is called a number A bit shifted to the left by B bit positions. And similarly with the right shift, same idea. The number A is bit shifted to the right by the number of bit positions. And so what it would look like here, we could write down, let's say, the number 5 bit shifted to the left by 4 bit positions. So if we work with just a byte, that's 8 bits. So we're going to look at the number 5 is going to look like, oops, let's get this right here. So the number 5 will be 0, 0, 0, 0, because there's nothing in the upper nibble, and 0, 1, 0, 1. So that's what you start with. So we've got our number 5 is here. That's 5 in binary. And then we're going to shift it 4 positions to the left. So all of this is going to move 1, 2, 3, 4 to the left. So this 1 here is going to be 1, 2, 3, 4. It's going to end up over here. So 0, 1, 0, 1. And then when you're shifting, what gets shifted into the end here is zeros. And so the rest of this is going to be 0. So all I've done is taken this group of bits here and moved them over to this position here. And that's what a bit shift left looks like. You can do a bit shift right the same way. Say we put a number up in here, we can put the same bit combination 1, 0, 1 here. Well, let's work with what we've already got here. So we've got this number now. We're going to bit shift it to the right 4. Now this number is 50 hex, and we're going to shift it to the right by 4 positions. We're going to end up with what we started with. So that's what bit shifting is about. If we have this number here bit shifted to the left 0 positions, because you can put a 0 in here as well, it doesn't change. It becomes that number there. Now I'm going to use this a lot in manipulating bits in a single register. But what I'm going to be shifting here, instead of 5, I'm simply going to be shifting 1. So if we put down a 1 here, 3 and a 1. So we always start with 1. So it's going to be 1 bit shifted to the left X number of times. So if we bit shift it 0 times, it doesn't change. If we bit shift it 1, it moves to here, 2, 3, 4, 5, 6, and 7. And if you have a bigger number, 16 bits or whatever, you can keep going. And remember, each time that you shift it to the left, a 0 gets shifted in. And as I said, similarly you can shift to the right. What I forgot to mention is if you're going to take this number and shift it to the right, zeros get shifted into the upper end as well. And that's a very useful operator, and I'll show you how I'm going to use it for manipulating the bits. Now in the compiler that I'm using here, there's a macro that's called BV, or bit value, and it looks like this: underscore B, capital V, and inside there's a number. And what it means is exactly this: 1 left shifted X positions. Very useful operator, and I'll show you in the code how to actually do it, or how to actually use it. The right shift operator gets used too, but I'm not going to talk about that right now. It's the left shift operator which is the most important one for what I'm going to demonstrate to you as well in the software. Now there's a couple more operators that I want to talk about. They're called the AND operator and the OR operator. And their symbols are, the AND uses the ampersand, which I'm not very good at drawing. That's an ampersand. And the OR uses a vertical line like this. Now they operate again on the bits of a byte or a word or whatever. And I think the best way to explain how these each work is I'll just drop a little truth table. So with the AND we're going to compare bit by bit. And so how can we do this here? Let's start with 2 bits, a bit A and a bit B, and then the result. We'll call it Y. So we'll make a little truth table that looks like this. I just want to get every combination of bits. And so when you AND, we're going to AND these 2 bits together, A and B. I'm going to do it a bit at a time and I'll give you the result here. So if we AND a 0 and a 0, the result will be a 0. If we AND a 0 and a 1, the result is still 0. And if we AND a 1 and a 0, the result is still 0. If we AND a 1 and a 1, the result is 1. So what this means is that you will always get a 0 whenever you've got a 0 in one of the two operators here. In order to get a 1 out, you have to have both of the inputs to be 1. That's the AND. The OR looks a little bit different, and we'll do it the same way. We got your inputs here, and we got our output over here. And again, the inputs will look just like this, like in the AND. So the output with an OR, so 0 ORed with 0 will give you a 0. 0 ORed with 1 will give you a 1. A 1 ORed with 0 will give you a 1. And a 1 ORed with 1 will give you a 1. So in this case here, if either one of these is a 1, then the output will be 1. In this case with the AND, if either one of these is a 0, the output will be 0. And the only time you can get a 1 with or a 0 with an OR is when both the inputs are 0. So that also is a very useful function. Now, typically how we use these is that we want to, if we look at a register, a microcontroller register, and we want to look at just particular bits in there. Say we want to test that an interrupt bit has been set in a particular register. So the registers in the ATmega 328 are all 8 bits. They're all 1 byte wide. So let's look at, say a particular register has, I'll just mark these as X's because they could be 1s or 0s. I'm just giving an example here, and say this is the bit that we're interested in here. And that's all the bits here, 1, 2, 3, 4, 5, 6, 7, 8. So, and I want to look at what the state of this bit here is. I don't know what it is. And so what I can do is AND it with a special number, what's called a mask, that will mask out this one bit and ignores all of these other bits here. Now remember, we used an AND, so excuse me, wherever there's a 0 bit, there will be a 0 in the result. But wherever there's a 1 bit, you will see the state of that bit. So what I'll do is I'll make my mask, we'll have a 1 here at the bit position of the bit that we're interested in, and all the other bits will be 0. So remember what an AND is. If there's a 0 in either one of these things, the result will always be 0. So you'll see a 0, a 0, and a 0 here. Then we'll look at these last three. The same again, always zeros. And whatever the state of this bit here that we don't know of, because of the 1 here, it will be this value in here. So if this was a 1 here, we would see a 1. If this was a 0 here, we would see a 0. So this thing here is called our mask. So that's one way of checking that, we're checking a particular bit. And we could check any number of bits in here by just simply putting 1s in the bit positions that we're interested in. If we want to, sticking with the AND function, so this is an AND function, if we want to make a bit in a register a 0 bit and not affect any of the other bits in that register, we can do it in a similar manner. So again, we have the same register here, say, and we want to affect this bit. We want to make this bit become a 0. And so what we'll do is we'll make our mask, we'll have it all 1s, except for the bit that we want to make a 0. Or bits, it could be more than 1 bit, depending on what you're trying to do. So when you AND this mask, this is another mask, and I'll be using this a lot, with our register, and put the results of that ANDing back into that register. So wherever we get a 1 here, whatever the value that was here in the register, it will remain the same. So if this was a 1 here, 1 and a 1 is a 1. But if this was a 0 here, 1 and a 0 is a 0. So this result is never changed. But when we get over to this bit here, we've got a 0 here. So a 0 with anything, 1 or a 0, will always produce a 0. And so this bit will always get cleared. But all the rest of these bits are unchanged, so we can read that register, AND it with this mask, and then put it back into that register. And that way we've cleared that 1 bit. Now there's another thing we could do if we want to set a bit in a register. We use the OR function. So again, let's use the same example. We've got this register. We don't care what those bits are. But this is the one that we want to make it into a 1. So in the same manner, we're going to read this register, and then we're going to OR it with a mask, and then put that value back in again. So if we look at here, now we want to make this bit a 1. And so how do we keep the same state of the bits here as they were originally? Well, you look back and you put a 0 in here. So our mask is going to look like this. A 0, 0, 0 here, and a 0, and a 0, and a 0 there. So when you OR it with whatever's in there is going to show up again. It's not going to get changed. So a 0 and a 0 will be a 0, but a 0 and a 1 will be a 1. And then in here we want to set this bit, so we make this a 1. So our mask is going to look like this. And so we OR so we read the register, and then we OR it with the mask, which sets this one bit, leaves all the other bits alone, and then we can write it back to that register. And that way we've made a change to that particular bit in the register, but we have not affected any of the other bits. And again, same with the AND, we can put numerous ones in here, and forever one that's any one of these that's a 1, that bit will get set. Now, keep this in mind. This is the OR function here. Keep this in mind, and when we look at the software, how I've written the code, because I'm using both of these, actually all 3 of these here. Well, no, not really. I'm not using this reading a bit yet. I'll show you probably in another video I'll show you how to read a bit using a mask, but I want to set or clear a bit by using these ANDing and ORing masks. So we'll have a look at our software and see how that's done. Alright, before we have a look at the software, I just want to go back to the schematic and show you what I/O pins that I chose to use. And they're plugged into Arduino pins 2, 3, and 4, which corresponds to port D pins 2, 3, and 4. And so that's important to remember. Now let's go to ML Studio. And I created a new project, just as I showed you in the previous video, but you go to New Project, select GCC executable, type in the name you want. I called it Blink 3. Browse for the location of where you want to put it, and click on OK. It creates the main.c file, which has the main function in it, and that's all you're going to need again for this project. It's a very simple project, so we only need one file. It automatically includes this library, which you need to use on every every Atmel processor that you use. You will have to include this io.h because it just defines all of the port register, or all the registers and everything that you need to know that you need to program, all the different registers that you'll have to program, and it copies the spec sheet or the data sheet exactly. I'm going to use delay again like I did the last time, so I included the util delay.h, and you can see down in the code here I've got delay in several places here, and I'm using the same delay time for each one, and it just defines how long the LED's turned on for, and how long it's turned off for. And it's used in about 6 different places, and I wanted to play with that value to make it look good, and I didn't want to go through and have to edit 6 or 7 different places in my software to change the same number. So I just defined this constant here, blink delay, and I made it 500 milliseconds. So here's our main function again, like I talked about in the previous video. Now the first thing we're going to do here is this line of code, which is our data direction register, DDRD. So it's port D, so we're using data direction register D. And I need to make those 3 I/O pins inputs. And then the next statement here is I'm making all of those I/O pins low. Now you can see some kind of cryptic looking stuff here. These port D4, port D3, those are predefined. Again, they're defined in this library here, so you don't have to define it yourself. And if I click on it, you will see that port D4 is defined as the value of 4. And port D3 is defined as the value of 3, and 2 is 2. Now I talked about previously in this video here, there's _BV function, which, like I said, is the same as the left shift operator shifting a 1 to the left. So what this means here is we're going to shift the 1 left 4 positions. So this is going to go into bit position 4, and there will be a 1 in bit position 4. In here, in this one here, we create another 8-bit value that is got a 1 in bit position 3, and over here we've got another byte value with a 1 in the bit position 2. And what I did describe previously in this video what the OR function is. Well, it's just this vertical line here, and on my keyboard that is shift backwards leaning slash. On my keyboard it's right next to the enter key, just above the right shift key, and that's how you type in that symbol. So what I'm doing is ORing this byte with the 1 bit in the bit 2 position, with this byte with a bit in the bit 3 position and the bit 4 position. When I OR them all together, I'm going to get a single byte with bits 2, 3, and 4 set, and all the other bits are 0. And then I'm going to OR that with whatever is in DDRD, in the data direction register. Now let's go back quickly to the schematic. In this very simple demonstration, I'm not using any of the other pins on the I/O, so I don't really, or on this port D, so I don't really care what happens to them. But in a real project, you may have other devices or other things hooked up to these other pins in here, and you don't want them to be affected. You don't want the data direction register to be affected. You don't want the value on the output pins to be affected by whatever you're doing to these 3 pins here, 2, 3, and 4. I don't want 5, 6, or 7, or 0, or 1 affected by what I'm doing with just these 3 pins. So I have to do it in this cryptic manner. So what I'm doing here is I'm creating this 8-bit byte with the 3 bits set. And remember, when a bit is set in the data direction register, the corresponding pin is an output. And so I'm reading the data direction register. That's what this OR equals means. So I read the data direction register, and then I OR it with this new byte. And what that does is it will set those 3 bits, only those 3 bits in that register, and then I write it back. So whatever the other bits that I didn't set, I didn't affect, were, they remain unchanged, and I just simply write them back into the register, and nothing happens to those ones. So I'm only affecting the 3 that I want to affect. Similarly, in this next statement here, port D, now I'm writing to the actual pins. I want to make them go low. So I'm using the AND function. Remember, as I said, when you AND something with a mask, that's how you make a 0. When you OR something with a mask, that's how you make a bit 1. So here I want to make these bits 0. So I take this. These are actually the same as what was used up here. I'm creating a 8-bit word with only bit 4 set, or bit 3 set, or bit 2 set. But what I'm doing here is I've got to change the polarity of those bits. And this little symbol here, the tilde, which is, if you look on your keyboard at the number keys across the top, and just to the left of the key, at least it is on my keyboard, it may not be the same on everybody else's keyboard, you will see another key that has the tilde on the top, and you have to shift and press that key, and that will give you the tilde. And what the tilde does here is it tells the compiler to take this word that you've created by left shifting the 1 bit, so we only have 1 bit set, and I'm going to convert all of those bits into the opposite polarity. So all the 1 bits will become 0, and all the 0 bits will become 1. And I do that the same with all of these. So now what this is, after you've done the tilde here, this is going to look like all bits are set except for bit 2, which is a 0. And the same thing with this one, and the same thing with this one. And then I'm going to AND them all together, and the result will be all of the bits in that byte will be 0, will be set to 1, except for bits 4, 3, and 2, which will be 0. And then that value is taken and ANDed with the value in the port D register. and then written back to the port D register. So wherever there was a 1 bit in this mask, if you want to call it that, the bits in the port D register will not be affected. I'm only affecting the bits 2, 3, and 4. Now, I'm probably guessing that for a lot of you people that are watching this video, this is really weird, really difficult to understand. But this is the way you really need to program. Rather than sitting here trying to figure out which bits you need to set and clear in these registers and manually typing all the ones and zeros. My philosophy in writing software is I want to allow make the compiler do most of the work for me, instead of me sitting around trying to figure out which bits I should set and clear. And there's a good chance that I could create an error that way, and then I might be scratching my head for a while trying to figure out why my software doesn't work. Whereas when I do it this way, the compiler figures out what bits to use and what bits to set and clear. I will be doing this a lot in my software. This is a more advanced way of programming, but is a much better way of programming once you understand how to do it, and it's a much less error-prone way of doing it. So that being said, you'll see that I've done that on every one of these things here. So what I'm doing in this while loop, so this is the loop in my main function that executes forever. So once the processor gets into this loop, it will never leave it until you turn it off or reset it. So what I'm doing here is I have to set, initially I set all of the data direction pins for the data direction register for those 3 pins. I made them all outputs. But remember when I described how this works, one of them has to be an input, because if it becomes an output, it can affect some of the LEDs that you don't want to be turning on or off. So what I'm doing here is making pin D2 an input. Sorry, pin D2 an output. And yes, I know I already did that here, but because when I come around from the end of this loop here, it is actually an input because of something I've done here, and then when I come back around the corner here and do this again, I've got to make sure it's an output again. So the first time through this loop, it's correct, and I'm just overdoing something here, rewriting what's already been done up here. But, or sorry, for port 3, not port 2. Anyways, that's what I've done here. So what I've done is I've made port 2 an input and port 3 an output, which it already is because of the first time through, but port 3 was made an input down here, and then when it comes back around again, you got to redo it. And then I make port 3 or pin 3 low and pin 4 high, and that turns on one of the LEDs. Then I delay for 500 milliseconds, and then I simply switch D3 and D4 around, so the D3 now goes high and D4 goes low, turns on the other LED. I'm done with that, those 2 LEDs, so now I got to switch to another port. So I'm going to stick with port 3, but I'll go to port 2 now. So I've got to make port 4 an input so that it's not going to affect anything, and then I make port 2 an output because I made it into an input up here, and then I simply make port 2 low and port 3 high, and that turns on one of the LEDs. I delay, switch the 2 around, so port 2 is now high and port 3 is low, and the other LED turns on. I delay, and then now I'm going to use the pins 4 and 2 this time. So I've got to make pin 3 an input, so it's not going to affect anything else. Make pin 4 an output because pin 4 was an input over here. And then I work with pins 2 and 4. I make 2 low and 4 high, turns on one of the LEDs. I delay for a period of time. Reverse that, turns on the other LED, delay. And then what I've done here is I've just turned everything off. So I made port D low, so everything's low now. And so none of the LEDs will light. So it turns all of the LEDs off for 500 milliseconds. It hits the end of the while loop, goes back to the beginning, and it starts the whole process over and over again. And so that is how I was able to blink those 6 LEDs in sequence the way I showed you at the beginning of this video. Very simple, but what I wanted to show in this video was how to manipulate the pins of a register or of a variable. You could do the same thing with variables. You can affect certain bits without affecting any of the other bits by using these AND and OR functions or operators, as I showed you before, as I talked about at the beginning of this video. Now, all this program is doing is blinking LEDs, so it's not that hard to do, and the microcontroller is wasting a huge amount of its computing power in these functions here: delay, millisecond, blink delay. So this is like a rabbit hole. The processor goes down into this rabbit hole and it hunts around for 500 milliseconds doing nothing except timing out, and then when it comes back it continues on. Now, if you've got other things going on in a much bigger project, you don't want to be wasting processor time delaying like this. You might need to be doing something else. And so in my next video, I think it will be, I'm going to start looking at the timers. I'm going to look at timer 2 or timer 0. There's 3 timers in an AT Mega: timer 0, 1, and 2. They all work kind of the same way, but they're a little bit different, and I plan to go through each one of them in detail, so you understand how they work. But I'm going to use timer 0 to create the delay without wasting time. The timer does the timing. The processor can go off and do other functions, and then it gets interrupted by the timer when it times out after, say, 10 milliseconds. And then you can count that 10 milliseconds as one, and you count 50 of those 10 milliseconds, and it'll give you 5 millisecond delay. And you maintain a counter. And anyways, I'll go through more detail in my next video on how to use a timer to set this time and allow the processor to go off and do something else. Let me just quickly look at some of the output files. So I go over to the Solution Explorer here, and one of the files I want to have a look at right now before it gets more complicated is this .lss file, and this is what's called the list file. And if we open it up, and what it does is it shows you the actual instructions that the compiler has decided to use to make your program function the way you've written it. And each instruction is stored in a memory location in the flash, and that's what actually gets burned into the flash when you program it. And this file here, the .elf file, is the file that it contains excuse me, it contains, among many other things, there's a whole bunch of stuff in the ELF file. You can look this up on Wikipedia. It shows up there and it describes what an ELF file is all about. It's the file that gets used by the programmer to program your code, but it also contains all of this stuff. But this is the list file, and it tells you where it's put the instructions and what the actual instructions are. And your processor, after you reset it or power it up, it starts at address 0 in the flash. And so at address 0 it has a jump to address 68. And that's what's called the reset vector. And all of these here are the interrupt vectors. And each location here, address 48, C, 10, 14, 18, 1C, etc., contains a different jump to a different address. And each one of these is for a different interrupt. So when timer 0 interrupts, it'll go to one of these addresses. When timer 1 interrupts, it goes to a different address. When the serial port interrupts, it goes to yet another different address. When you create a interrupt service routine, there's a special way of doing that. The compiler knows that it's an interrupt service routine, and it fills in the address of that function that you create for the service routine and puts it in here so that it jumps to that particular address. You notice that they're all 7C except for the first one here. This one is always the interrupt vector, and it always vectors to somewhere in the code. It's automatically done by the compiler. These ones here are 7C, which is what they call, in this case, a bad interrupt. So if something happened, if you enabled an interrupt for some reason without actually having an interrupt service routine, there's a way of catching that. And if we look at where 7C is, which is down here, it is simply jump to the location 0. It'll just jump back to the reset, and it'll reset your microcontroller, and it'll start going as if you had just powered it up. So if any of your interrupts are enabled by some reason, you've screwed up in your code, but you haven't written an interrupt service routine for it, this is what will happen. We'll just automatically reset the microcontroller. Well, address 6.8, so jump to 6.8 when we go to our reset vector. And this is where it shouldn't go to any of these. It should only go to this one here. And then what it does is it tells it to jump to here. And what it's doing here is initializing variables in this part of the code here. When it finishes here, it's going call 0 or call 80, and that's our main in loop, or our main function, which is here. Now, if somehow you write your main in such a way that it drops out to this curly bracket here, which is the end of main, main will exit. It's written just like any other function, although you don't want main to exit. This is a throwback from personal computers and bigger mainframe computers that there were multi-users, and your main did execute or exit at some point, because you had to give control back to other users who were using the same computer as you. But on a microcontroller, nobody else is using it, just you, and so you don't want main to exit. But if you screw up in your code and main does exit, it will, what happens to it when it drops through? Yeah, and so it'll end up here at exit, which means clear. This CLI instruction means clear interrupts, and then it just simply jumps to this location and it just hangs here forever. Stop the program. The microprocessor is still running, but it's not doing anything except humming, sitting here on this location, always reading this jump instruction, always going back and reading the jump instruction again, and going back, etc., etc., etc. It'll stay in here forever until you turn the thing off or hit the reset button. But you don't want it to do that, because obviously when it's sitting here, it's not doing anything else. It's wasting time. But it's put here as a safety measure, so that if something happened and caused your main routine, your main function to exit, you don't want to go off and execute some weird code and maybe it's running something and it turns a motor on that it shouldn't do, or whatever. So the idea is to trap the processor here so it doesn't do any damage. Let's go back and just quickly look at some of the... So here's int main. It puts the C code in here just to tell you where it's at. So this is the first C statement that I had here, and this is the assembly code that the compiler did to execute this here. Now the compiler looked at this part of the statement, and it figured out what the actual value should be, and it turned out to be 1C hex. So what the compiler told the microcontroller to do here is in register 4 address 0A. So it went to address 0A, which is our DDR-D register, address 0A. It read the value of that register and put it into a register called register 24, and then it ORed it with this value, and then it wrote it back out, register 24 into address 0A. So this did exactly what I asked it to do here. I asked it to read this register, OR the value with what I've got here, and then write it back. Same with port D. The instructions look very similar, except I'm doing an AND. Reading register or address B, which is port D, into R24, and it with whatever the compiler figured out what this value was going to be, and then write it back. So anyways, just a quick little peek at some of the behind-the-scenes stuff. Have a look at this file whenever you get a chance, and it's if you're writing code and you're having a problem trying to figure out the code's not working and you can't figure out what the bug is, sometimes it's good to have a look at this and see what it's actually doing. Of course, the bigger your project gets, the bigger this is going to be and the harder it is to look through it. So I think I'm going to stop here. I don't want this video to be too long, and I want you to work through this. I will leave the code that I've written for you on my GitHub site. I'll leave a link to that down below in the comments, and you can try it yourself. And stick around for the next video. I think I'll do it on timer 0. Please be aware that I don't have a script, and I haven't figured out exactly what order I'm going to do my videos in. It's just going to come up as it comes up, as I feel like how I'm going to do this. And I think a nice segue from this video is into timer 0, using it to make timing instead of using a wasteful delay function. So anyways, hope you liked the video. Stick around, check out the next one I've got. Thanks for watching.